Let's start. A supernova is not one thing. It's a category of cosmic disasters that can happen for totally different reasons. Two explosions can look similar in the sky, yet one is a thermonuclear detonation, and the other is gravity crushing a star's core like a soda can. There are two big families. 1. Type Ia, a white dwarf goes boom. 2. Core collapse. A massive star's core fails, collapses, and rebounds. Also, the naming has one simple rule at the top. Type 1 equals no obvious hydrogen in the spectrum. Type 2 equals hydrogen is present. Then the letter after that tells you what kind of type 1 you're dealing with. Type Ea, the thermonuclear one. A white dwarf is basically a dead star's core, Earth-sized, insanely dense, and held up by quantum mechanics. On its own, it's stable. The problem starts when it has a close companion star. The white dwarf can steal gas from that companion, or two white dwarfs can merge. Either way, the dwarf gains mass and gets hotter and denser. When conditions cross a tipping point, carbon fusion ignites everywhere at once. Not a gentle burn, a runaway chain reaction. Result, the whole white dwarf is shredded. No neutron star, no black hole, just expanding debris, and a flash bright enough to outshine an entire galaxy for a short time. In spectra, type Ia typically show a strong silicon signature, which is one of the clues astronomers use to separate Ia from other no-hydrogen explosions. Why you should care? Type Ia explosions are unusually consistent in peak brightness, so astronomers use them as standard candles to measure cosmic distances. If the universe had a measuring tape, Ia supernovae are the nearest thing to printed ruler marks. Now the other family, core collapse supernovae. These happen to massive stars, the ones that spend their lives fusing heavier and heavier elements. They can fuse hydrogen, then helium, then carbon, oxygen, silicon, until they build an iron core, and iron is the dead end. Fusing iron doesn't release energy, it costs energy. So once the core becomes iron-rich and heavy enough, the star can't support it. Gravity wins. The core collapses in a fraction of a second, crushing protons and electrons into neutrons. The collapse slams to a halt when neutron pressure pushes back, and a shock wave races outward. That shock, helped by a flood of neutrinos, is what blows the star apart. What's left behind is usually a neutron star, and if the core was massive enough, a black hole. Core collapse types are labeled mostly by what we see in their spectra. Think of it as what chemical fingerprints show up in the light. Type 2, hydrogen is present. If the spectrum shows hydrogen lines, it's type 2. That means the star still had its hydrogen envelope when it died. Type 2p for plateau. The light curve stays bright for weeks because the expanding hydrogen recombines and releases energy steadily. It's like the explosion is paying its power bill in installments. Type 2l for linear. It fades more smoothly without a long plateau. Type IIN for narrow lines. The blast is slamming into a thick cloud of gas around the star, so you get sharp spectral features and extra brightness from that violent collision. It's a supernova with bonus fireworks. Type IB, no hydrogen, but helium is present. If there's no hydrogen, the label switches to type 1, but not all type 1 are Ia. This is where people get confused, so here's the shortcut. Ia is thermonuclear. IB and IC are core collapse. Type IB happens when a massive star lost its hydrogen envelope before exploding. Maybe strong stellar winds stripped it, or a companion star stole it. The spectrum shows helium lines, meaning helium is still there. Type IC, no hydrogen and almost no helium. Type IC is an even more stripped star. Hydrogen is gone, and most of the helium is gone too, exposing deeper layers of the star. Some of the most extreme IC events are linked to long gamma-ray bursts. That's when the collapse launches narrow jets, moving near light speed. If one of those jets points at Earth, we see an insane flash of gamma rays. If it doesn't, we just see a powerful supernova, and never know we missed a cosmic laser show. Quick cameos, the rare, weird ones. Superluminous supernova. These are ridiculously bright, sometimes 10 to 100 times brighter than normal. Possible engines include a newborn magnetar, a supercharged, rapidly spinning neutron star, dumping energy into the debris, or intense interaction with dense gas. Pair-instability supernovae. In extremely massive stars, high-energy photons can convert into electron-positron pairs, which reduces pressure support. The core partially collapses, fusion runs wild, and the star can be completely destroyed, no remnant at all. Electron-capture supernovae. For stars in a narrow mass range, electrons get captured by nuclei in the core, removing pressure support and triggering collapse. It's a quieter, why did physics suddenly turn off, route to explosion. So here's the entire cheat sheet. Type Ia, white dwarf, thermonuclear, nothing left behind. Type 2, core collapse with hydrogen. Type IB, core collapse, no hydrogen, helium present. Type IC, core collapse, no hydrogen, little or no helium. And the special editions, superluminous, pair-instability, electron-capture. If you can remember one rule, remember this. The letters mostly tell you what layers the star still had when it died. That's it. If this helped, hit like, subscribe for more fast-paced breakdowns, and drop a comment. Which supernova type sounds the most terrifying to you?